My name is Hua Zhou. I'm local here at UCLA. I'm a faculty in the Department of Biostatistics and also Department of Computational Medicine. So today, my plan is to give a review of some attempts by my colleagues and I to analyze massive longitudinal and genetic data in Biobank. So I will roughly follow the order of the papers I gave in the CGSI program. So first I will review a method we developed called WISER for analyzing massive longitudinal data in EHR. And then the second project is how we applied this WISER approach to do genomics, to do genomic scan on longitudinal biomarker. So that method, that's what we call the trajectory GWAS. And then, depending on time, I will discuss some extension of these ideas to jointly analyzing longitudinal and survival data in biobanks. So that's roughly the plan for today. Okay, so the first piece of work, the WISER, it's majorly done by my former student Chris German, who was co-advised by Professor Jensen Sinsheimer and myself. Also, we are working with my colleagues, Dr. Hua Zhou, on this project. So actually, this project started with a very, very simple questions Dr. Hua Zhou and her collaborator asked. So they have done lots of work on diabetes care. So essentially, what one biomarker they are studying a lot. They publish a lot on this biomarker. It's called glycemic variation. So essentially, as I understand, is for diabetes patients, of course, glucose the higher, the worse, right? We need to control the glucose level to be low. But what they found is it's not only the glucose level, it's also the variation. So it's not only the level, that's also the fluctuation of the glucose, which matters a lot. So they publish lots of papers on this area. And then their simple question is, say, now we have the data, we have access to all these biobanks which are linked to electronic health records. We have those longitudinal data. Can we use this data to answer the question, what are affecting the glycemic variation? Is that, of course, diet, certain food is causing glucose to rise very rapidly and then lower very rapidly. Which cause lots of fluctuation than other food, and also exercise, of course, but also medication. To treat diabetes patients, severe patients are using insulin, but before that we have like 3 or 4 major kinds of oral medications. Are certain medication better than other in terms of course they are all controlling glucose level, but are certain medications better than other for controlling the variation? So based on those EHR data in Biobank, are we able to answer this question? Also, another big question is there any genetics? Are there any genes which are causing my fluctuation is much larger than yours? So those are the questions they asked, which motivated this first work. Just as a motivating example, this is a famous clinical trial in the diabetes care world. So it's called the ACCORD trial. In this trial, they randomize patients into 2 arms. So one arm is standard treatment arm. That's this line. So on the x-axis, those are the longitudinal visits, the follow-up visits of the patients. Okay, and then each dot is like the average glucose level at that visit. All right. So this is a standard treatment. So the glucose level is being controlled as the target level is 7.5, okay? So that's one arm. The other arm is the patient, it's more aggressive. So the target glucose level is controlled at 6.5. So the question this clinical trial is trying to address is say, can we be more aggressive in controlling glucose level, okay? Because in general, the lower level, it's better than long-term outcome. Okay, so that's ACCORD data. It's about 10,000 diabetes patients. All right, and but we want to. This is a clinical trial which was already done like 10 years ago. But based on this data, we want to know is there any way based on this data we can model the variability? So this is classical longitudinal data. And do diet, medication, or genetics, exercise, all those factors, how do they influence the fluctuation? So that's what we want to use this data set to answer. So here, 10,000 patients, it's too much to display. So we just randomly drawn 100 patients. So these are just something called a spaghetti plot because it looks like spaghetti. So each of the red curve is one patient in the standard treatment arm, and each of the blue curve is an intensive treatment arm. Okay, so we can see, visually we can see some patients where first we can see there's a difference in the mean level, right? In general, the standard treatment arm, the red arm is higher. It's a 7.5. The blue curve are 6.5. So there's a difference in the mean curve, but also visually we can see some patients the fluctuation of the glucose is larger than others, and we want to know what are causing that. Okay, so that's what we want to illustrate using this example. Okay, so actually after we started thinking about this glycemic variation, then we found actually it's not a totally esoteric topic. There are lots of other traits people not only care about the mean, but also care about the variability. For example, blood pressure. So of course, the higher blood pressure, it's very bad for CVD outcome, but also the fluctuation. So if our blood pressure go high and low, like violently, it's not good for our health. Also heartbeat. If our heart beats, the rate change a lot, the fluctuation variability change a lot, it's not good to our health. Also the sleep variability, also outside the medical area, like in public transportation systems, there's a reliability, which is variability of the transport time. So for example, if I take a bus from point A to B, some days it takes 15 minutes, other days it takes 45 minutes. If the variability is high, it's called less reliable in the public transit system. Also in finance, another big area people care about the fluctuations of finance. If the stocks fluctuate so much, it's called volatility. That's a subject under intensive study in finance, of course. So it's not a totally isolated topic. So our goal is we want to come up a model which can model the mean of the biomarker, but also the fluctuations, the variability. Okay, when we look at the literature a couple of years ago, we found in medical literature the dominant method is something like so you have lots of longitudinal trajectory of the biomarker over time, right? And the most people are using in their paper is they just based on each curve, say this blue patient, this is blood pressure measured over time. What most people do is they just calculate a summary statistics, say standard deviation of this blue curve. Just calculate simple standard deviation or some other summary statistics. For example, CV. What's CV? It's correlation of variation. Coefficient of variation. It's another common usually metric for variability, right? So they calculate a summary statistics summarizing how much fluctuation in this curve. Then for each person, we have a fluctuation metric, and then they regress that on genetics or medication or not. Okay, so that's most people are doing a couple years ago when we checked the literature. Okay, but the one thing we quickly realized is it's just too crude, this method. For example, in this blue patient. So this guy's blood pressure is increasing over the time. Then this patient started taking medication. Then the blood pressure get lowered. At the same time, the fluctuation becomes smaller, right? One thing we don't like is this heuristic method is, for example, like medication status is changing over time, right? So that's exactly what we want to model, right? We have the EHR data. We know this patient is not taking medication in the first couple of years, started taking certain medication. We want to model that. if we just calculate an overall standard deviation or CV, we cannot model that. That's the issue, right? So then we start thinking about how can we model that. So if you are biostat students, I do see some students from my department here. In biostat students, there's one class usually you take, it's a longitudinal data analysis, right? And one standard model we use for longitudinal data is something called the linear mixed model. It's a very standard model, okay? So here, yi, it's a vector. Essentially, it's that curve in the previous slide. It's just a biomarker measured over time, okay? And we want to know how certain things are changing that curve up or down. So that's what's in the X. So those are the features, the predictors. So you can have genetics here or medications there. And those can change over time, okay? And the beta are the effects, how those features are shifting that curve up or down, all right? And then and the second term, it's why this model is called a mixed model, because the first effect, the beta, is called fixed effects, okay? The second term, again, Zi are some features, could be time fixed or time varying, but the effects, gamma I, we don't assume it's fixed, we assume it's random, okay? We don't see it, okay, gamma I. And then we have the typical noise term. Noise term is just a fluctuation around the mean of that curve, okay? So that's a typical linear mixed model. Okay, so what are the parameters? The parameters in this model are beta. Beta are the fixed effects, right? How certain features, say certain gene, is shifting the curve, all right? And gamma I, remember, the random effects, we don't see it, right? We assume, usually, textbook assume it's from multivariate normal with mean 0 and a covariance matrix sigma sub gamma, all right? And this is the parameter. So it's the covariance matrix of random effects. It's a parameter we need to estimate. And typically, people call this parameter the between subject variability, because what this parameter is capturing, so we have lots of curve. Each person, you have the EHR, it's a curve, and then this sigma sub gamma is capturing what's the variance of the intercept, what's the variance of the random slope. So essentially, it's capturing how variable are between each curve. Okay, so the name, it kind of makes sense. It's called between subject variability. Okay. And then another parameter is this sigma epsilon square. So that's just the variance of the noise term, all right? So the key assumption in the classical RMM is the noise variance, it's constant. It's constant over time. It's constant across individuals, okay? So essentially what it's assuming is the little fluctuation here, it never change over time, okay? It's always sigma epsilon square. And also, it's the same between each curve. Each longitudinal curve, the little fluctuations, the variance, it's exactly the same. Okay, so that's being assumed in this very classical linear mixed model. Okay, so that's why this sigma epsilon square, it's also called within subject variability. So that's capturing the little fluctuation within each curve. And remember our original question by clinician and so on. That's exactly. They want to know how this thing, sigma epsilon square, is changing over certain features, okay? Like medication, exercise, diet, or genetics, all right? So that's a model. So once we understand the sigma epsilon square, it's the stuff, it's the parameter we want to model, it's very easy to extend this classical linear mixed model to a model which is called a mixed-wide model, okay? So essentially, we no longer assume this noise variance. That's little fluctuation around each curve, right? We no longer assume that's constant. We model it. So we say the sigma epsilon square we just use a straightforward exponential link. It's modeled against a third set of covariates, Wij, okay? Again, if you want to know, is there any genetics which changes the fluctuation, you can put here in the W, all right, or diet and so on, all right. So the effects for the within subject variability, it's called tau in our model. And also we add more heterogeneity because we assume the baseline variability within subject variability, it's different. It's allowed to be different between different subjects. Okay, so that's a model called a mixed wide model. Okay, actually there's also a software out there, so it's not a totally new model. There's even a software there. It's called mixed wide. So that's the first thing we tried, but immediately we ran into an issue, which is I'm trying to use this table to explain. We just simulated one data set. It's just simple data set, 1,000 individuals. On average, each individual has 10 longitudinal measurement of a biomarker, and you know it's just a smallish longitudinal data set, and then we want to run this mixed wide model. We want to know certain features are affecting the little fluctuation of each curve. And I want you to focus on the runtime that's in the last row. Immediately we can see the mixed wide program takes really long, even on this data, only 1,000 individuals, okay, longitudinal data. And what's the reason? The reason is because of random effects, as all we know. So here we have some, like at least one or two, or even more, if you have you want to model more complex random effects. So we have a few random effects here. We have another random effect here, and then if you use MLE to do the model estimator, you need to integrate out those random effects. But we know numerical integration is expensive, right? You can do one-dimensional, two-dimensional, three-dimensional numerical integration is okay, but more than that, good luck. It takes, there's a very severe curse of dimensionality issue for numerical integration. And this mixed wide software is using MLE, so which means it's using numerical integration. That's why it's so slow. Of course, there's also Bayesian method, but the Bayesian method is even slower than MLE here. Okay, so that's the issue we run into. Even for this 1,000 individual moderate data set, it can take like from model 1 to model 3. These are slight variation of this model. It's either like a 45 minutes, just fit one data set, up to 10 hours. So that's one data set. But the data set we want to handle, these are the data sets we want to handle. First, we want to do genomic scan. So UK Biobank, we want to analyze the variability of 11 biomarkers, blood pressure, lipids level, glucose level, and so on. We want to know, are there any genetics in the mean of the trajectory and the variability of the trajectory? And you can see the sample size in UKB, the minimum is like 50,000, like for glucose measurement, or up to 150,000 sample size. So that's the sample size we want to handle. And remember, we want to do GWAS. We want to fit this model for like millions of genetic markers. So apparently that method is not going to work just because the computational challenge. Other data sets we are working on is the VA MVP project. That's another biobank. And for VA population, we know there's diabetes is the instance is pretty high. It's the MVP project essentially is a genotype of 1 million veterans, and 30% of those veterans have diabetes. So the sample size we want to handle is 300,000. Again, think about the runtime for 1,000 sample size. If we don't do genetics, say we would just want to study the effects of medication and so on, then we don't need genetics. The whole VA primary care data set in VA system, there are 3.7 million diabetes patients. So these are the sample size we want to handle. Okay, so we quickly realize where MLE is not going to work. We need something fast and correct. Okay, so that's the method wiser. We can see at least we cut the runtime from like hours to like less than 1 second. Okay. So that's kind of motivation. Now, what's the approach? Well, approach is MLE is expensive, and the Bayesian method is expensive. We have to go back to some more simple estimation method. So the first method that we tried is method of moment, because under that linear mixed model, even we model the within subject variability, it's very simple to calculate the first two theoretical moments. The first moment, the mean of the biomarker trajectory, it's just simple. It's just this. And the covariance of the longitudinal measurements of biomarker, it's given by this formula. This term is same as the classical linear mixed model. What changed is this term. In the classical linear mixed model, this term is constant. It's a constant sigma epsilon squared times the identity because it's assumed it's never changes the fluctuation. In our case, it's changing. So we, instead of a constant diagonal matrix with constant diagonal terms, the diagonal terms now it's changing. Okay, so you can calculate what are on the diagonal theoretically. Okay, so that's the formula. Okay, so this is the covariance of the trajectory. All right. Now you have the theoretical two moments. We just need to match the sample first moment and sample second moment to the theoretical one. So here we just use simple least square criteria. Okay, that's the first method we tried. Okay, so immediately you can imagine we are going to run into one issue because people like MLE. That's a recommended approach because it's efficient, which it's optimal, right? In some sense, if all the model assumptions are met, MLE is efficient, right? We lose efficiency if we use other method. So that's what we saw. For estimating the mean parameter beta, actually least square, like this approach is okay. But estimating the variance components, like the tau, that's effects on the within subject variability, and also this variance component, actually even at moderate sample size, the estimate can be off. Okay, so that's one thing we observed using method of moment. Okay, so we need one fix. Okay, so what's the fix? Actually, the idea is also very simple. If we even not longitudinal data class, if we just take a linear model, you start, it has all the assumption. One assumption is a linear mixed model assumes the variance, it's a homogeneous, the variance is the same. But then in the later section or chapter, we learned if it's heterogeneous, we can improve the estimation efficiency by something called weighted least squares, right? So that's the idea, exact same idea we apply here. So instead of the a straightforward method of moment, we do weighting, okay? And how do we weight the first estimation equation? For estimating beta, we are going to use the variance to do the weighting. It's just like the weighted least squares, but now it's longitudinal. We need a covariance matrix to do the weighting, okay? Now, how do we get this covariance matrix? Well, we can first apply the method of moment to get a very crude estimate of tau and the sigma gamma, okay? So we have a crude estimate. We know it's not that accurate because the method of moment is not efficient, but we can use that as the weighting to improve the estimation efficiency, okay? So that's the weighted version for the beta, for the fixed effects, okay? Now, it took us a while to figure out how to do the weighting for the second estimation equation for variance components, okay? So essentially, what we did is the second estimation equation, it's a residual about the second moments, right? It's natural to use the fourth moment. So to derive the fourth moment, let's assume the biomarker is multivariate normal, and then we use the fourth moment of multivariate normal to do the weighting. After some simplification, we end up with this formula, which is actually looks not that bad, okay? But remember, for the method to work, we don't really need distribution assumption. All we need is a moment assumption. We just need the first two moments, okay? But to do the weighting for the second estimation equation, we use a working distribution assumption. We assume it's multivariate normal. But again, it's not changing the theoretical consistency of the estimate, okay? So that's overall, this approach is what we call wiser. Again, the idea is very simple. It's essentially method of moment, but with weighting to improve estimation efficiency, okay? And you can do this a couple rounds. For example, first we do just a regular unweighted method of moment to get the VI, which is a crude estimate of the covariance of the trajectory. And then we do weighted estimates, and then we improve estimate for the VI so you can repeat a couple rounds. In our software, I think the default is 3 rounds, but in practice, usually just 1 round waiting or 2 rounds are already give us very good estimate, okay? Just to summarize, this method is, first, it's very fast because we are not doing numerical integration, we are not doing Bayesian sampling. It's super fast. That's what you saw. Instead of hours, we just need a split second. Also, theoretically, it's consistent. It's not efficient because MRE is efficient, but remember, it's a trade-off. We sacrifice efficiency for something called robustness. Remember, our method only need to assume existence of the 2 moments. Okay. The distribution, you don't need, classical linear mixed model. You assume Y, given the random effects, it's multivariate normal. Random effects are multivariate normal. You put lots of assumptions in the classical linear mixed model. We don't need that. Our method, in some sense, is robust. Okay, so that's the advantage of the WISER approach. So this table is the same 1,000 sample size example. We just want to show how weighting helps. Maybe it's simulated example, so we know the truth. So the tau 5, the true value is 0. Method of moment, it's this estimate. We don't know it's good or not, but we just do 1 more round of weighting. Then we find the estimate is much closer to the truth. Okay, so here it's just showing the weighting improves the estimation efficiency tremendously, at least for this data set. Okay. All right, so that's pretty much the essence of this WISER approach. Remember, just to recap, it's a method for modeling not only the mean of the biomarker trajectory, but also the fluctuation. I can show you examples of what this model tells us. Computational, I'm skipping it. There's some trick to make it really fast. Okay. So far, I just talked about the estimation, but then we know we need a confidence interval and a p-value for those doctors. Since it's an estimation framework, we just use classical sandwich formula to get the standard error. All right. So, okay. So in the paper, we did at least 3 examples where I think we didn't put all these examples in the paper. The first one is a smart device, the wearable device data. Okay, so wearable device, remember, it's measuring, let's say, Apple Watch. It's measuring our heart rate every 5 minutes, right? So it's intensively measured longitudinal data. Okay, for this data set, there are this many subjects and totally this many observations. This method takes about half a minute. Accord data, that's the data, 10,000 diabetes patients and longitudinal measured glucose level. It takes half a minute. There's a third example which is kind of interesting because when before Trump was banned from Twitter, everybody says whenever Donald Trump tweets, the stocks just becomes more volatile. We don't know whether this is true or not, but we can get the data. So Chris German scraped all the Donald Trump's tweets over the period of 3 years, and the stock prices over the same period. All right, the sample size is 505 because we only focus on Fortune 500 stocks. All right, and then the features in the model are like the words, what kind of words in Trump's tweet. A certain word will cause the stocks to be more volatile. Okay, so that is the example. But to show the example in the Accord data, just to illustrate what exactly this model is giving us. Okay, the beta is just the usual regression coefficient we are very familiar with. Let's focus on the last 5 predictors. So those are the in that Accord data set, these are all the diabetes medications the patient is using. Severe diabetes patients, we know they have to inject insulin, right? And these 4 are the 4 oral diabetes medication. If you look at the beta, they are all negative, which makes sense because they are treating diabetes. Of course, they are lowering the glucose level. Okay, so this all makes sense. The beta coefficients, right? it's more interesting to look at the tau. So that's the extra information this model is producing. Remember, this is at the log scale because we use the exponential link, right? First, it's very well known for injecting insulin. It's causing lots of fluctuation of the glucose. This is very, very well known. So it's reflected by this positive tau effect size with very, very high significance, okay? What's more interesting is about this medication study with S. I don't know exactly how to pronounce it, but it's a second line oral medication for treating diabetes. And when we talk to clinician, we ask, does that make sense? Because we are a little worried. This effect size is 0.3. It's positive and it's highly significant. So actually, clinician says they are very aware of. That's one reason this is second line medications. They don't because they believe, clinicians believe it has more side effects and so on. So actually, it's shown here this medication is causing. Well, it's a regression model. I shouldn't say causing. It's more associated with higher glucose variability, so which is reflected here. So other three oral medications, they are all reducing the variability of the glucose. So that's what this model is. The kind of information this model is yielding. Okay, so Trump-Tooth data, I'm going to skip it. Some words are causing, like if he mentions China, then it's more, it's going to fluctuate more, the stock prices, okay? So I do realize I'm running out of time. I think I have until 10, but just quickly, I can take a little bit more time. Oh, okay, yeah. So, but still, I want to respect next speaker. So, so that's the first project. Again, it started a very simple question. Our collaborators is asking, given this great EHR data nowadays very available, can we study the effects of certain factors like medication and so on variability, not only on the mean, but also on the variability. Okay. The second project essentially, we want to know, is there any genetics in the fluctuation of the biomarker? Okay. Again, the major challenge is still computational. You know, again, WISER is great. We reduce the runtime from hours to like 0.3 second, but still remember the GWAS, when we run GWAS on let's say UKB. You know, remember the sample size ranges from 50,000 to 150,000. And remember, we have like 10 million genetic markers, right? Imputed variance, usually it's like 8 million or 10 million. You need to fit that WISER on like, for one biomarker, you need to fit on like 10 million genetic markers. So it's a lot of computing. But then a few tricks we try to address this computation burden. One is the score test. As we all know, you see lots of modern genetic GWAS tool, they all do score test. One reason is you don't need to refit the model for each genetic marker. So you just need to fit WISER on the null model. So you include all the stuff, principal components, age, gender, those things. You fit once without genetic marker, and then given that fitted model, you can do very fast score test on each genetic marker. So that's the first thing we did. So then again, for imputed data or sequence data, you know, you encounter very rare variants, and the type 1 error is not properly controlled. You need to calibrate it. So a common technique is SPA, saddle point approximation. We need to implement to get the proper type 1 control level for rare variants. So those are some technical issues we need to address to apply WISER to GWAS. Okay, and then we apply the tool, and the software we call trajectory GWAS. It's on GitHub. Okay, overall, for example, just to give you an idea of the computational efficiency, to analyze the SBP, if you remember the sample size after data cleaning, it's 150K individuals in UKB. The median number of SBB is the systolic blood pressure. The median is relatively more. I believe you can go to the previous table. I believe it's 15 measurements, the median number of SBB measurements in UKB. To analyze that data on 10 million genetic markers, imputed variants, it's 150 CPU hours. So you can, I believe we split into a chromosome, so it's essentially overnight, okay, to fit one biomarker. Okay, so that's the status for this project. Okay, genetics. Okay, so also maybe just another 5 minutes, just extending the idea. So far, I just talked about the longitudinal data, which is widely available in EHRs, right, in Biobank. But I haven't talked about survival data. Why survival data is important? Because so far we just talked about the model for modeling the biomarker, right? So let's say glucose. So the patients come to the hospital and then say the diabetes patient get HbA1c glucose level measured. So we do have this trajectory of the biomarker over time. But remember, what doctors care is what? What doctors care is, okay, I see your glucose is either getting worse or improving. Based on that information, I want to predict, okay, so my sense is in 3 years you develop some diabetes complication, say retinopathy. In 5 years, the chance you develop retinopathy is, let's say, 0.3 in 3 years, okay? And in 5 years, maybe it increases, it's 0.5 and so on. So essentially, doctors more care about the survival curve, okay? So they want to know how soon, given this trajectory, how soon you are going to develop a certain outcome, major health outcome. Sometimes it's death, the major outcome. So that's the ultimate question we want to answer, right? We want to use the model to maybe mimic or emulate doctor decisions, right? So we want to do something called dynamic prediction. So we see the EHR evolving over time. Dynamically, I want to update my prediction of many health outcomes. So that's what we ultimately want to achieve, okay? So in statistical literature, there is a little word where it's not that little, it's actually 20 years at least, development of a field. It's called joint modeling, okay? So essentially you have longitudinal biomarker and you want to dynamically update the survival probability of health outcome, okay? So here I'm presenting one specific setup in the joint model, okay? So the first two equations, it's exactly the Weiser model, right? I have a biomarker, let's say glucose. So this is the mean model, and also we are modeling the fluctuation because we learned from lots of previous work, the fluctuation matters a lot. It's a strong predictor, risk factor for lots of health outcomes. So we do want to model that. So that's the first two models, okay? But where's the survival? That's where the third equation is coming from, okay? If you take a survival class, you spend lots of time studying something called a proportional hazard model. That's not the model we are using here for a reason. I will explain in a few seconds. So we are using an alternative model. It's called accelerated failure model, AFT model. It's also very popular. Not as popular as Cox proportional hazard model, but it's also people are still also using this AFT model. Okay, so AFT model is modeling the time to event. Okay, so let's say time to development of complication or time to death. All right, but the time is positive, so we take log. So TI, it's a log of time, and then we put a model there. So these are the X tilde is the effects for affecting the survival time. But then how the longitudinal model is linked to the survival model, so that's the next two terms, okay? So remember in the longitudinal model, we do have random effects. So we have this gamma I, and then we have this omega I, right? And these random effects are shared with the survival models. That's how these two processes, the longitudinal process and the longitudinal model, how they are coupled together, okay? It's called a shared random effects model, all right? And how strong is the association between these two processes? That's reflected by this association parameter nu, and this scalar nu here. These are also parameters to be estimated. They measure how strongly this longitudinal biomarker is affecting the survival time. Okay, so that's one setup for joint model we are working on. Okay, and the reason we use AFT is we want to extend the idea we used in WISER. Remember, in the WISER, the idea is very simple. It's a method of moment, right? So we want to get our hands on moments, right? This is just a linear model for survival time. It's very easy to derive moments. If we use Cox model, everything is based on hazard. It's not that easy to get the moments. Okay, so that's the fundamental reason we use AFT. Okay, but also personally I like AFT model because the interpretation is so simple, right? When you explain people the Cox model, usually you need to explain what's a hazard, right? That takes, hazard, remember the definition, that's a limit. It's not that easy to explain to doctors. But AFT, it's very easy because the AFT model is just turning the biology clock faster or slower. So if you have a mutation, then your clock is turning faster. The exponential of the effect size is just essentially how fast you are turning the clock, right? As people often say, a dog's age, you multiply by 7, that's equivalent to like a human age, right? So the interpretation is as simple as that, the AFT model. So I also like the interpretation of AFT model, all right? And then given that, you can derive the theoretical moment if there's no censoring. Remember, survival is hard majorly because the censoring. You don't actually see the event time for lots of patients because of the loss of follow-up and so on. So if there's no censoring, then you can just same exercise. You can, based on that model of the 3 equations, you can get the first 2 moments. You can do the method of moment. But the survival, we have censoring. How to handle that? We're using a technique, it's called a synthetic variable. So essentially, based on the data, you can construct something called a synthetic variable, which has the property, the synthetic variable, based on the observed data, which is potentially right censored, you can construct such that it shares the same moments as the original uncensored data, event time, okay? So there is a small literature there. We need to extend that because we need literature is about the first moment synthetic variable. For our method, we also need a second moment, so that you need to generalize that technique to construct something called a second moment synthetic variable and so on. So use that to construct synthetic variable, and then you can just use our WISER method. Essentially, it's a weighted method of moments. So that's the technique we are using to handle both longitudinal biomarker and the survival time. All right. So I'm skipping all the details there. But once we handle, again, the reason we want to use the method moment is because the computational challenge. Again, joint model, there's an existing literature. But if you run the software, you won't be happy if you want to analyze crazy like UKB or MVP data. Even just 1,000 sample size to fit a joint model using existing software, it's overnight, okay? But now we address the computational challenge, then we can extend to lots of different directions. For example, multiple biomarkers. So we know, say, for major health outcome, we know it's not only sufficient to look at one single biomarker, say glucose. We need to look at lipids, trajectory, and so on. And we need to incorporate all those multi-biomarkers to do the dynamic prediction, all right? So we are working on multi-biomarker, also functional data. So recently, our group is working a lot on the wearable device for diabetes patients. It's called a CGM, continuous glucose monitor. So that's every 5 minutes you have a glucose reading. So that's a patch. Every 5 years, you get a glucose reading. So based on that intensively measured data, how can we do the joint model? So we are trying some functional approach for the longitudinal part, and so on and so forth. That's what we are working on now. So I do apologize. I'm 15 minutes over, but I will stop here. Thank you very much. Yeah.